What if a model could understand and translate language without any recurrence or convolutions at all? Attention is all you need introduces the transformer, a sequence model built entirely on attention, promising faster training and strong accuracy by rethinking how sequences are processed. Why rethink sequence models at all? Most translation systems at the time relied on recurrent or convolutional networks with an encoder-decoder setup, often boosted by an attention layer to connect the two. The transformer goes further. It removes recurrence and convolutions entirely and uses attention everywhere. That design makes computations across all positions in a sentence happen in parallel, which dramatically speeds up training while maintaining a strong ability to capture relationships between words. In head-to-head tests on standard machine translation benchmarks, this approach delivers better quality and trains faster. It reaches 28.4 BLEU on WMT 2014 English-German, surpassing prior best results, even model ensembles, by more than 2 BLEU. On WMT 2014 English-French, it sets a new single model mark of 41.0 BLEU after 3.5 days on 8 GPUs, only a fraction of the compute used by earlier top systems. The takeaway: attention alone can power a state-of-the-art translator, and it scales efficiently. Why were recurrent networks the default for years? Because they read sequences step by step, carrying a hidden state that, in principle, can remember what came before. Gated variants like LSTMs were designed to better preserve long-range information, and encoder-decoder architectures became the backbone for translation. One network compresses the source sentence, another generates the target, and attention helps the decoder focus on the most relevant source words at each step. As researchers stacked deeper models and refined training techniques, performance climbed, but recurrence still limited parallelism and made long dependencies harder to handle efficiently. This context sets the stage for a model that keeps the strengths of attention without the bottlenecks of recurrence or convolutions. Why do recurrent models bog down on long sequences? Because each step depends on the previous hidden state, you must compute them one after another. That serial dependency blocks within-example parallelism. Tricks like factorization and conditional computation can reduce the amount of work or activate only parts of the model, but they don't break the need to wait for the prior step. As sequences grow, memory limits also prevent simply offsetting this by batching many examples at once. Attention helped models connect far-apart tokens directly, no matter how distant they are in the sequence. But in most systems, attention was attached to a recurrent backbone, so the sequential bottleneck remained. Only a few models tried to drop recurrence entirely. Practically, this design reaches top translation quality after roughly 12 hours of training on 8 P100 GPUs, thanks to computations that run in parallel instead of step-by-step. Next, we break down how self-attention alone can power both the encoder and the decoder, and why this choice improves efficiency and long-range reasoning compared with recurrent or convolutional designs. How does a sequence-to-sequence model turn one sentence into another? The encoder first converts every input token into a continuous representation that captures its meaning in context. The decoder then generates the output one symbol at a time, each step conditioning on what it has produced so far. This auto-regressive setup lets the model maintain coherence and follow the structure of the target language as it writes. The transformer keeps this encoder-decoder blueprint, but swaps in stacks of self-attention and simple position-wise feed-forward layers on both sides. Self-attention lets each position look across the entire sequence to gather the most relevant information, while the feed-forward layers transform those attended features independently at each position. Stacking these blocks builds deep, expressive representations. The figure shows the encoder on the left and the decoder on the right. What's inside each encoder layer? 6 identical layers are stacked, and each layer has 2 parts. First comes multi-head self-attention, which lets the model look at the sequence through multiple views at once, capturing different types of relationships in parallel. Then a position-wise fully connected network refines each position's features independently, adding nonlinearity and mixing information within the token's representation without blending positions. What story does this diagram tell? It maps the full path from tokens to predicted words. Inputs become embeddings, then gain a sense of order through positional encodings. The encoder repeats the same pair of steps multiple times, that NX label. Multi-head self-attention to mix information across positions, followed by a position-wise feed-forward network to transform each position separately. Each step is wrapped with add and norm blocks, which stabilize learning by combining the new computation with the original signal and then normalizing it. The decoder mirrors this stack but adds 2 twists: a masked self-attention block that forbids looking ahead, and an attention block that consults the encoder's output to pull in source-side context. During training, outputs are shifted right so the model learns to predict the next token from only past outputs. Finally, a linear layer projects to vocabulary logits, and softmax turns them into probabilities. Why don't signals get lost as they pass through many layers? Each sublayer adds its transformation to the original input, a residual path, then normalizes the result. Conceptually, the residual path preserves a clean highway for information and gradients, while layer normalization keeps activations well-scaled and comparable across features. To make these residual sums legal and consistent, every sublayer and the embedding layers emit vectors of the same size. D_model equals 512. This uniform shape lets the model stack many layers without shape mismatches or unstable scaling. How does the decoder use the source sentence without peeking at future targets? It inserts a dedicated attention sublayer that looks at the encoder's outputs, letting each target position draw exactly the source side details it needs. At the same time, the decoder's self-attention is masked so a position cannot attend to later target positions. Combined with the shifted right targets during training, this enforces strict left-to-right prediction. Each token is predicted using only earlier outputs plus the encoder's context. As in the encoder, every sublayer is wrapped with residual connections and layer normalization to keep learning stable. Imagine posing a question to a set of memories. The query is your question, the keys describe what each memory is about, and the values hold the content you might retrieve. Attention scores how well the query matches each key, converts those scores into weights, and then forms a weighted combination of the values. The result is a context vector that emphasizes the most relevant information for the query. This mechanism lets the model dynamically focus on what matters at each step. How does the model measure match efficiently? It compares a query to all keys using dot products, which act as similarity scores. These scores are scaled to keep them in a sensible range, then pass through a softmax to produce attention weights. Applying these weights to the values yields a focused summary tailored to the query. Because all queries, keys, and values are processed in batches with matrix multiplications, the whole operation is fast and highly parallel.
We are Genipad. Your likes and subscriptions inspire us to create more videos and keep improving our service. Want to turn your own content into videos? Visit us at www.genipad.com.
Ever wonder how attention turns comparisons into useful context? The diagram walks through the pipeline. Queries compare with keys to produce scores. Those scores are scaled to keep values stable, and optional mask blocks forbidden positions, and softmax converts scores into weights. The weighted sum over values produces the output. Multi-head attention runs several of these pipelines in parallel, concatenates their results, and uses a final linear layer to fuse them into one representation. What actually happens inside an attention block? The left panel shows one scaled dot product attention pipeline. The right shows many of them running in parallel as separate heads. Running several heads at once lets the model look for different patterns simultaneously. For each query, we compare it to all keys to get similarity scores, scale those scores to keep them well-behaved, then apply softmax so they become a probability-like set of weights over the values. The output is a weighted sum of the value vectors, tailored to that query. Instead of processing queries one by one, we stack them into a matrix Q and do the same for keys and values into K and V. A single matrix multiply computes all query key scores at once, and the result maps neatly back to an output matrix whose rows correspond to the input queries. This batched form is fast and hardware-friendly. Conceptually, you build a table of similarities between each query and every key, normalize each row so the weights sum to 1, and then use those weights to mix the values. Doing it with matrices makes the entire operation parallel and efficient. Are all attention mechanisms the same under the hood? Two common variants differ mainly in how they score query key pairs. Additive attention uses a small neural network per score, while dot product attention scores with a simple inner product. Although both have similar theoretical complexity, dot product attention maps directly onto optimized matrix multiplications, making it faster and more memory efficient in practice. There's a catch with unscaled dot products. As the dimensionality of queries and keys grows, the scores tend to grow in magnitude. That can push softmax into very sharp regions, leaving tiny gradients and unstable learning. Dividing the scores by the square root of the dimension tames their scale, keeping softmax responsive and gradients healthy. Why split attention into multiple heads? By projecting queries, keys, and values into several lower dimensional spaces, the model forms H-parallel attention layers. Each head can specialize in different patterns or positions. Their outputs are concatenated and passed through a final linear layer that blends these perspectives into a single vector. This design lets the model attend to multiple kinds of relationships at once. With only one head, those perspectives get averaged together, and distinct signals can blur. Here's the intuition behind the scaling step. When query and key components are roughly independent with unit variance, the variance of their dot product grows with dimensionality. Bigger dimensions produce larger typical scores, so scaling keeps the softmax in a stable operating range. Why split attention into multiple heads? Conceptually, we first map the queries, keys, and values into several smaller subspaces, run attention separately in each one, then stitch the results back together and mix them with a final linear layer. This lets different heads focus on different types of relationships at the same time, and the last projection blends those perspectives back into a single representation of the original size. These projection matrices are learned linear maps that reshape the model's representation into lower dimensional query, key, and value spaces for each head. Choosing smaller per head dimensions lets each head specialize while keeping the overall size manageable. A final output projection then recombines the concatenated head outputs into the original model dimension, so downstream layers see a single, coherent vector at each position. We use 8 heads each with 64-dimensional queries and values, so their concatenation returns to the model size. Splitting the model dimension evenly this way keeps computation roughly on par with a single head setup, while the multiple heads provide diverse views that often translate to better signal extraction with similar cost. Where does attention show up in the transformer? In 3 places. Self-attention in the encoder to contextualize the source sequence, self-attention in the decoder to build the target sequence step by step, and encoder-decoder attention so the decoder can selectively look back at the encoded source. Each placement serves a distinct role in understanding inputs and generating outputs. Encoder-decoder attention connects generation to understanding. Each decoder position queries the entire encoded input so it can pull in exactly the source information it needs at that step. Encoder self-attention lets every token in the input see every other, producing rich, globally informed representations of the source. Decoder self-attention is similar but masked to preserve autoregressive generation. Each position can only use information from itself and earlier target tokens. Practically, the mask zeroes out illegal connections before the softmax, so probability mask cannot flow to future positions. Together, these 3 attentional roles enable the model to comprehend the source globally, generate coherently, and align source and target on the fly. Attention mixes information across positions, but how do we transform features at each position? With a position-wise feed-forward network, the same small MLP is applied independently to every token. It expands the feature dimension, applies a nonlinearity, then projects back, giving the model a powerful per-token transformation between attention layers. Functionally, this block takes each token's vector, maps it to a higher dimensional space, applies a nonlinearity to introduce feature interactions, and compresses it back to the model size. This deepens the model and adds nonlinearity without coupling different time steps, which keeps it highly parallelizable. Although the same transformation is used at every position within a layer, each layer has its own parameters. You can think of it like 2 1-by-1 convolutions with a ReLU in between, expanding from 512 to 2048 units and then returning to 512 gives the network more capacity to re-express features, improving what the subsequent attention and feed-forward blocks can do. How do raw tokens become probabilities for the next word? Tokens are first mapped to dense vectors by learned embeddings of size equal to the model dimension. After processing through the decoder, a learned linear layer followed by a softmax converts the final representation into next token probabilities. The same weight matrix is shared between the input embeddings, output embeddings, and the pre-softmax linear layer, tying the input and output spaces together and reducing parameters. The embeddings are also scaled to keep their magnitude in a stable range, which helps optimization. With no recurrence or convolution, how does the model know word order? It adds positional encodings to the token embeddings so each position carries information about where it occurs in the sequence. These encodings can represent absolute or relative positions and are added element-wise to embeddings at the model's input, giving attention the clues it needs to reason about order. Which layer type gives you the shortest route between distant tokens and the most parallelism? This table lines up common sequence layers, self-attention, recurrent, convolutional, and restricted self-attention, and compares 3 things that matter in practice: how much compute each layer needs, how many steps must be done sequentially, which limits parallel speed, and how many hops information must travel between any 2 positions. Shorter paths make long-range relationships easier to learn, and fewer sequential steps unlock faster training. Here's the big picture in the numbers. Self-attention directly connects every token to every other in one shot, so it needs only a constant number of sequential steps and offers the shortest information paths. Recurrent layers process tokens one after another, which forces many sequential steps and yields the longest paths. Convolutions are parallel across positions, but spreading information far away requires stacking several layers, so path length grows with depth. Restricted self-attention trims the cost by letting each token attend only within a local window. This speeds things up on long sequences, but increases the number of hops needed for distant interactions. In short, self-attention maximizes parallelism and minimizes path length. Recurrence minimizes pairwise compute, but bottlenecks on sequential execution. Convolutions sit in between. Restricted attention trades reach for efficiency. Positional information is added right where the model starts processing tokens, at the bottoms of the encoder and decoder. These encodings are the same size as the token embeddings, so they can be simply added element-wise. They can be learned or fixed. This paper opts for a fixed design built from sine and cosine waves at different frequencies, chosen to encode both absolute and relative positions smoothly. Conceptually, each coordinate of the positional code is just a sinusoid, and adjacent coordinates form sine-cosine pairs at the same frequency. Think of it as giving each position a unique multi-scale fingerprint. Because sinusoids are phase-shifted by moving along the sequence, the model can infer how far apart two positions are using simple linear combinations, handy for attention to reason about relative offsets. The frequencies span a geometric range from very short to very long wavelengths. That mix captures fine-grained local order and broad, long-range structure at once. A key benefit is that shifting by a fixed number of steps corresponds to a linear transformation of the code, letting the network compute relative positions without complex machinery. They also tried learned positional embeddings and saw similar accuracy. The sinusoidal version was kept because it generalizes more gracefully to sequence lengths not seen during training and avoids adding extra parameters. Why choose self-attention over recurrent or convolutional layers for turning one sequence into another? The authors compare these options as building blocks inside encoder or decoder stacks, focusing on how they shape efficiency and information flow. Two practical yardsticks are highlighted. First, computational complexity per layer, which affects raw cost. Second, how much can be parallelized. The fewer sequential steps a layer needs, the better it scales on modern hardware. The third yardstick is the path length between any two positions. Shorter paths mean signals, gradients, and dependencies don't have to travel through many transformations, making long-range relationships easier to learn and more stable to train. Putting it all together, self-attention links all positions in a constant number of sequential steps, while recurrence requires processing the whole sequence step by step. In many NLP settings where sequences aren't extremely long relative to the embedding size, self-attention is also computationally favorable. For very long sequences, you can limit attention to a local neighborhood to cut cost, accepting a few extra hops for distant interactions while still keeping good parallelism. What happens if we limit attention to a small neighborhood around each position? You save computation, but you also make it harder for distant words to influence each other. Information then has to hop through several intermediate positions, and the worst case number of hops grows with sequence length divided by the window size. The authors flag this local attention trade-off as a promising direction to study further. Why don't simple convolutions solve long-range dependencies out of the box? A single convolution only blends information within its kernel window, so distant tokens can't interact unless you stack many layers or use dilation. Dilated kernels spread reach faster, but you still need depth to connect all positions. Computationally, convolutions tend to be heavier than recurrent layers as kernel width grows. Separable convolutions help by splitting spatial and channel mixing, cutting costs substantially. Even so, when you push kernel sizes large enough to cover long contexts, the total compute ends up comparable to running one self-attention layer plus its pointwise feed-forward network, while still lacking the direct all-to-all connectivity self-attention gets in a single hop. A bonus of self-attention is that it's easier to peek in to what the model is doing. Different attention heads often specialize. Some track CO reference, others align verbs with their subjects, or link modifiers to the right nouns. These patterns line up with syntactic and semantic structure, making the model's behavior more interpretable than many alternatives. How do you actually train a transformer to reach those results? This section outlines the practical setup: data preparation, batching, hardware, optimization schedule, and regularization choices that make training stable and efficient. The models are trained on standard WMT machine translation benchmarks. For English-German, the data includes roughly 4.5 million sentence pairs. The text is tokenized with byte pair encoding and a single shared source target vocabulary, so both languages draw from the same subword units. This keeps the vocabulary compact, about 37K tokens, and lets the model share statistics across languages. For English-French, the dataset is much larger, around 36 million pairs, and uses a 32K word piece vocabulary. Batching groups sentences of similar lengths so that each batch has about the same total number of tokens on the source and target sides, roughly 25K each. That minimizes padding and makes GPU computation more consistent and efficient. Training runs on a single machine with 8 GPUs. With the base hyperparameters, each step takes about 0.4 seconds, and training runs for 100,000 steps, totaling roughly 12 hours. The larger model is slower at about 1.0 second per step and is trained longer, 300,000 steps, amounting to about 3.5 days. Bigger models cost more per step, but often benefit from extended training to fully realize their capacity. They use the Atom optimizer with momentum-like terms tuned for fast, stable convergence, betas set to 0.9 and 0.98, and a small numerical epsilon to avoid division issues. Rather than a fixed learning rate, they adopt a schedule that starts low, ramps up, then decays, balancing rapid learning with stability. Conceptually, the learning rate is scaled by the model's dimensionality and follows a curve that first grows and then decreases with training steps. The early linear warm-up prevents the optimizer from taking steps that are too large before parameters are sensibly initialized by data. After warm-up, the rate decays proportionally to the inverse square root of the step number, which keeps learning going while reducing noise as training progresses. In practice, this means the learning rate climbs steadily for a fixed number of warm-up steps and then falls off smoothly. They set warm-up to 4,000 steps, which provides enough time for the model to stabilize before the decay phase, often yielding faster convergence and better final performance. To prevent overfitting and improve generalization, the training uses multiple regularization strategies. Residual dropout is applied at key points in the network. After each sublayer computes its output, dropout randomly zeros a fraction of activations before adding the residual connection and normalizing. This discourages co-adaptation of features. They also apply dropout to the sum of token embeddings and positional encodings in both encoder and decoder stacks. For the base model, the dropout rate is 0.1, which provides regularization without overly slowing learning. What if you could get higher translation accuracy while spending far less compute? This table sets up that comparison. It lines up BLEU scores next to estimated training cost, making it easy to see that the transformer delivers stronger results with markedly lower computational expense than prior systems. Here's what stands out. On English-German, the big transformer pushes BLEU to 28.4, exceeding even ensemble baselines, while the base model is already highly competitive. On English-French, the big model reaches 41.0, outperforming previously published single models and landing near ensemble results without their hefty compute bills. Across the board, the transformer's accuracy comes with substantially fewer training flops, showing much better compute efficiency than earlier architectures like recurrent and convolutional models, especially when those rely on ensembles to boost scores. Label smoothing slightly blurs the target distribution during training, instead of insisting that one token is 100% correct and all others are 0%. This discourages the model from becoming overconfident, acting as a regularizer. Because perplexity assumes one-hot targets, smoothing can worsen it. But the model generalizes better and becomes better calibrated, improving task metrics like BLEU that reflect translation quality rather than overconfidence. On WMT14 English-German, the big transformer sets a new high water mark with 28.4 BLEU, more than 2 points above prior bests, including ensembles. Training took just 3.5 days on 8P100 GPUs, underscoring that attention-only models can scale quality without a ballooning compute budget. Even the base model outpaces earlier systems at a fraction of their training cost. For WMT14 English-French, the big transformer reaches 41.0 BLEU, surpassing all previously reported single models while using less than a quarter of the training cost of the former state-of-the-art. For this setup, a lower dropout rate, 0.1 instead of 0.3, let the model make fuller use of its capacity without overfitting, which can be advantageous when the data or regularization needs differ from the English-German setting. To stabilize and slightly boost performance, they average multiple recent checkpoints, a few for the base model and more for the big model. This smooths out training noise and yields a more reliable predictor. Decoding uses beam search with a modest beam size of 4 to balance quality and speed. A length penalty counters the common tendency to prefer overly short translations, and a maximum output length tied to the input prevents runaways while still allowing longer outputs when needed. Decoding stops early when the model is confident it's done. They compare accuracy alongside an estimate of training compute by multiplying training time, the number of GPUs, and each GPU's sustained single precision throughput. This offers a hardware-aware but architecture-agnostic measure of training cost, making the quality versus compute trade-off clear across different models. To see which parts of the transformer matter most, they tweak one component at a time on the English-German dev set. Keeping decoding the same and skipping checkpoint averaging isolates architectural effects from training variance, so changes in BLEU more directly reflect the design choice under test. Varying the number of attention heads while holding total compute roughly fixed reveals a sweet spot. Multiple heads help because each head can capture different relationships in the sequence. But if you push to too many heads, each head gets too few dimensions, weakening what each can learn. With a single head, the model loses that diversity and drops about 0.9 BLEU compared to the best configuration. Curious which dials on a transformer actually move the needle? This table lays out a systematic sweep of architectural and training choices and shows how each one affects development set performance on English right-pointing Arrow-German. It reports both BLEU and per-word piece perplexity, notes when values deviate from the base setup, and makes it easy to see trade-offs between accuracy, model size, and training budget. What's inside the comparison? The grid varies depth, model width, feed-forward size, number of attention heads, the key/value dimensions, dropout and label smoothing levels, positional encoding type, and even training steps. For each configuration, it lists parameter counts alongside development set perplexity and BLEU, plus a larger big model for a capacity versus accuracy contrast. It's designed to reveal how capacity, regularization, and attention configuration interact, and where extra compute or smarter allocation pays off. A small attention bottleneck makes it harder to match queries and keys well. When the key/query dimension is reduced, the model has less room to represent what matters about each token, so dot product attention struggles to judge compatibility precisely. That's why shrinking DK costs quality and hints that richer compatibility functions could help. Bigger models generally win because they can represent more nuanced patterns. The catch is overfitting, which dropout counteracts by making the network rely less on any single path through its layers. Finally, swapping sinusoidal positions for learned positional embeddings yields essentially the same performance here, suggesting that for these data and lengths, both schemes provide sufficient position information to the attention layers. Where does attention go next? Beyond text, the same mechanics can align and integrate signals in images, audio, and video, but scaling to high-resolution or long-duration inputs calls for local or restricted attention, so compute grows gently with length. Another frontier is speeding up generation by reducing how strictly outputs depend on previous tokens, which could cut latency without sacrificing quality. These directions aim to keep the benefits of attention while making it practical for large, multimodal problems. The authors provide their training and evaluation code publicly to support reproduction and further research.